Okay, good day, IB Bio Online. Only kids, miss you guys. Really enjoyed seeing some of you on Zoom last Friday. I'll try to get one of those set up again this week. And you can always email me and set up a time to talk through Zoom or chat. Office hours are every day from 2 to about 2:30 or 2 to 3, and then also again on Fridays from 10 to noon. Just give me a little bit of warning so I can make sure I can get in front of there. Sometimes I'm setting up labs and everything here. But today, all I really wanted you guys to do is finish working on the frequencies, flatulent frequencies, and using the analysis. I did add a new chart here. You can use that one or use the one you were working on previously. I just added some stuff to this one. So if you click on this, it's got everything we did from before. So it'll just be an updated version of it, and you can delete the old copy. If you remember right, back on the first one, we analyzed 5 different trials of different types of beans and had calculated the flatulence per hour, or at least that's the data that was given to us. We went through how to set up spreadsheets, how to calculate mean, standard deviation, what standard deviation means, and talked about these error bars. And I want to start with the error bars because, as I told you before, the reason we use error bars is they give us some level of certainty. And for some reason, this error bar seems really, really big. I need to go check that because something is definitely not right there. And if you remember to do your error bar, since we're already here, got to go into Edit Chart, which might just make your computer freeze. There it goes. And then you got to go into the Customize range, Series, and we're going to go check that our pinto beans is right, and I have a feeling something's going on. Should be a constant at 4.6. That is correct. Okay. I guess I just had really big variance in that number. So what I want to do today is these error bars give us a good indication of, is there going to be statistical difference? The only one I can tell for sure that there'll be significant statistical difference is these two, because their error bars don't overlap at all. But on some of the rest of these, the error bars do overlap. So for example, between the black beans and the navy beans, there is some overlap. There's also a little overlap here, and there's a lot of overlap on this one. So there still could be statistical significance here, but it's not just blatantly obvious. And even when it's blatantly obvious, you're required to run a statistical test. So today we're going to talk about t-tests and maybe a little bit about the ANOVA test. Mr. Crouch should have gone over the chi-squared test with you, and we will use that as well at times. But I'm gonna, if you want to use that on your lab, if you need to, I will know what your data is going to look like, and I'll kind of hint you towards what statistical test to use, and I can give you some help on that as well. Both are fairly easy to do. So, as I was saying on our graph, we're never sure about our data in science, and we should always run a testicle test to see if there's cause or correlation. I want you to be very aware that most of us will never be able to prove cause. Cause is a very high place. So normally we're just looking for a correlation between things. That correlation may point to cause at some point, but be sure in your evaluations not to really push the idea of cause, because that's not good science. You know, we get some data. There could be a very strong correlation, but to prove cause, you really have to take out all other factors, all other confounding variables that can cause difference. So to go to cause means you've done a lot of research, and it's not very common that we get to that point, especially if testing on humans. For our data, a student's t-test or an ANOVA test would be best. You might even run both of these. You might run an ANOVA test, which will tell us for all the data, and then maybe a t-test to tell the differences between two variables. So a t-test tells us the difference between two variables, and that's what we're probably going to use. T-tests can be very cumbersome, but with Sheets or Excel, these become very, very easy. I'd also like you to know that other statistical tests that can be used are R values. So let's say you have all your raw data plotted out, and you have continuous variation for both, not discrete like we had with these, and you have a nice scatter plot and you get a nice trend line, you can calculate the R value on that trend line. Excel does it for you, so does Sheets. And that R value can be used as a statistical test. So the closer it is to 1, the more correlation there is. And there's like a level that says you have so much correlation on that as well. So that is a good statistical test. That means you don't have to do the rest of these if your data supports that. This data does not, and a lot of times data won't support that. And I talked about chi-squared tests as well. So I just want to show you guys how to run a t-test. And then we're also going to talk about writing a null and alternative hypothesis. So this was our data. I'm going to go ahead and copy this now. I would think it would be a good idea for you to copy it because I'm going to, I just wanted you to see the data, but I want to work with it below where I have a lot of space to do the calculations. And the calculations are going to be really easy. It's the writing null hypothesis and alternative hypothesis that will probably start driving you nuts because for this experiment, technically we should probably write about 10 of them. And that can be kind of boring. Your data, hopefully you didn't use 5 different manipulated variables here, and your manipulated variable is more like a, 1 can of beans, 2 cans of beans, 3 cans of beans, oh my God, 4 cans of beans I'd be throwing up. But maybe something like that where it's a gradient, and then you wouldn't have to run as many t-tests as this one. But in this one, you would want to compare each type of bean to each other. We're not going to do all of that. I'm just going to have you practice with a few. So we are going to use a student's t-test. There's actually 2 types of t-tests. There's a paired t-test and a 2-point t-test. And it compares the mean and standard deviations of 2 samples to see if there's a significant difference between them. In an experiment, a t-test might be used to calculate whether or not differences seen between the control and each experimental group are a factor of manipulated variable or simply the result of chance. So if you were to flip a coin 100 times, it should land on heads 50 times and tails 50 times. But we know that that's not the case because chance comes into play, and maybe there's a chance you got 90 heads. Well, t-tests kind of look at like, if you got 90 heads, what are the chances of that being to chance, or was there something wrong with that coin? And I think the chance of getting 90 heads would actually be a binomial distribution, by the way, but kind of same idea, easier to explain. The chance of that happening would be pretty low, that it was due to just random chance, like probably less than 5%. And if it's less than 5% chance that it happened due to chance, then we would say that's significant because chances are that's not the case. But 1 in 20 times that could be the case. So it's never perfect, right? In science, we should never say it's 100%, minus the fact that Mr. Moriarty is greatest teacher ever. No, that's never been scientifically proven and is probably totally not true. The t-test is a test of statistical significance. I'm sure you guys can read these. Difference between 2 groups. So we're always going to look at 5%. We want our chance of error to be less than 5% that this data is due to chance. So first thing we need to do in any significance test is there are 2 possible hypotheses, the null and alternative. So the null hypothesis right here is always going to be the means of the 2 variables are the same. There is no difference between the 2 variables. They do not change, okay? So in this case, beans and no beans, there is no difference if we were just testing beans overall against it. The alternative hypothesis would state the means of the 2 variables are different, okay? And you'd have to write these for your variables, what you're testing, or your 2 groups. The means of the 2 groups are different, or the means of the 2 groups are the same. And you always want to write out your null and alternative hypothesis, but really, really important, do not mistake these with your experimental hypothesis. This should only be in your data analysis and conclusion and evaluation. So at the beginning of your write-up, you're going to have an experimental hypothesis. In my case, it was eating beans increases the amount of flatulence in the body, human body, And this is because of some research I did. They have oligosaccharides that are unable to be broken down by the human body, therefore have to be broken down by bacteria in the large intestine. These bacteria use the oligosaccharides for energy and as a byproduct produce carbon dioxide and methane, which causes flatulence in humans. Okay, that would be a research hypothesis. Okay, at that point, that's a good hypothesis. In your analysis, after you do your statistics test, that is where you put in your null hypothesis and alternative hypothesis. So I'm going to write a null hypothesis for our whole lab. Or actually, I'm just going to pick one variable. I want you guys to practice on at least 2 or 3 of these, but I am going to compare, because the first ones we're going to do is pinto beans to no beans, okay? So those are my 2 variables. We're going to do our first t-test on these 2, okay? Ultimately, you'd want to do a t-test for all of it, and we could also, we're going to run an ANOVA for a t-test. Do beans make a difference to the amount of flatulence, okay? And I'll show you guys that. Pretty easy, actually. So the means of 2 variables are the same. Eating pinto bean, or you always want to highlight it. If you just do an H with a little O, it should be subscript, but I don't know how to do that on here, so you can change it in Word. This would be my null hypothesis, which means there is no difference. So eating pinto beans, or pinto beans, I'm going to make it this really simple, and no beans have the same effect on farts. Okay, that easy. That's my null hypothesis. Our goal with the statistical test is to prove that wrong. Typically, your alternative hypothesis lies within your research hypothesis, although sometimes that can be different depending on what kind of data you have. I mean, if you're trying to prove 2 things are similar, then we might have that flip. But normally, this would be close to your research. In this case, pinto beans and I messed up here. Pinto beans cause more farts than no beans. Technically, it could cause a different amount of farts than no beans, but we'll just say no beans. That works. Okay, that is our null and alternative hypothesis, and now we need to do our statistical test. So earlier, I had you guys copy that data table. I'm going to put that data table down in here, and we're going to practice running our t-test. So pick some squares. You always want to label above them what it is so you know this. Eventually, you're going to have to make this all look really nice in a document, but you can at least copy and paste from here. So the first one I want to do is the t-test of no beans versus pinto beans. Okay, because we're always comparing 2 variables. I'm going to go ahead, go up here and merge these 2 cells. Or no, I'm going to text wrap, just so it's nice and smooth for me. And here is how simple it is, and you guys need to follow along and do this at home as well. To run a t-test, we're going to hit equal. Start typing t-test. By the time you get here, you should come up with t-test. Returns the probability associated with the t-test. So what we're actually getting here is a p-value. We're not getting a critical value, any of that. We're just getting a t-value. If you don't know what a critical value is, really, I'm not going to worry about it right now. Wait till statistics class. We're just going to use a p-value. And p-value is the probability that this occurred by chance. Okay, or the probability that chance would occur in these results. So we're going to do t-test, and now we got to select our data. So I'm going to run pinto beans. It doesn't matter what order you do. Big thing, you have to use a comma. So notice I just put a comma in, okay, and then highlight your next data set. Comma again. We don't have any more data, but there are 2 types of t-tests, and so we need to identify which kind we're going to use. Number one, is it one-sided or two-sided? Always just use two. I doubt you're ever going to use a one-sided t-test. And then this next number depends on what kind of data you have. I'm just going to have you guys use 3 without a lengthy explanation. But 3 just means we can't assume that these are normally distributed, which kind of makes sense. And with this small of a population, that would be hard to do. And then you just hit enter, and we get a number. Okay, so this is our p-value, and I'm going to actually type that in here. Okay, so we have our p-value is 0.0348. Don't worry about how big that number is. I would even just decrease it. Okay, and that's saying that there is a 35% chance that this value was strictly due to chance, and these means could be the same. So over here, I'm going to give our instructions on what you do. If the p-value is greater than 0.05, that's 5%, then we fail, I'm gonna write that big, reject the null hypothesis. If the p-value is less than 0.05, we reject the null hypothesis. Okay, so this is big stuff. If the p-value is greater than 5, notice we fail to reject the null hypothesis. And then if it is less than 0.05, we reject the null hypothesis. So at 0.35, that is much greater than 0.05. So we would fail to reject the null hypothesis to this data. So fail to reject null hypothesis. I'm just going to do HO because it's easier. These are just little notes to myself. I'm going to fail to reject the null hypothesis. So what that means is I cannot, with this data, say that there is a difference between the amount of flatulence in pinto beans and the amount of flatulence with no beans. Okay. There could still be, that's why we fail to reject. We're not saying that it's impossible that there's a difference, but we're saying with the data that we've collected and the information here, there is no way that I can tell you that pinto beans cause more farts than not eating beans, not with this data, okay? Even though you go back and look at the graph, it looks like the mean is much, much higher than none because we have such long variance right here in statistical means. There's such a huge standard deviation. That's probably why we can't predict this one. So let's do a couple more and see if there is any that do. So maybe on our next one, we'll do the t-test between black-eyed peas and peas versus no beans. Okay, so we can do a test now to determine if that is. So I want you guys to go ahead and run that test. Do it on your own, because hopefully you're doing that, and I will do it along with you. So t-test. Okay, and then I'm going to highlight the data I want. This time I'm doing black-eyed peas, comma, no beans, comma, 2, comma, 3, and hit enter. Oh, much different p-value this time. So with a p-value of 0.0026, which thing should I do? Okay, so this time we're going to reject the null hypothesis, which pretty kind of means we're saying that there is evidence here. The data shows that there is a correlation between more farts with eating black-eyed peas than not eating any beans at all. Okay, so here we have significant data to make a point in our evaluation. On this one, we would have to mention this in the evaluation, but we would say that there is not significant evidence that there is a difference between the two. Here we would say there's definitely significant evidence, okay? And then we could run the same thing for black beans versus no beans, navy beans versus no beans, all of those. And if we go back and look at our graph again, the black-eyed peas to no beans, you can really see they don't have any overlap at all. Okay, so there was a really good chance that there's statistical difference between them. I would say the same thing between navy beans and black-eyed peas. But here's one where, hey, there is some overlap, but maybe there's not enough. Ooh, let's look at this one. Black beans versus no beans. There is some overlap here. Okay, so this is one where I'm questioning, is there statistical difference or not? It's going to be really close. And the only way we would know is to run a t-test. So let's do the t-test for black beans and no beans. I want you guys to go ahead and run that test. Okay, and hopefully you guys all got the same number. Check yourself if you didn't. And this time it is 0.03, which is less than 0.05. So we would reject the null hypothesis. And even though they were really close, we do see that there is statistical reasoning to believe that black beans do cause more flatulence than no beans. So there is a statistical difference between this data and this data for the mean. Okay, hopefully you guys are getting a good idea of how that works. I am going to exclude pinto beans from this, but I want to show you guys a ANOVA test too. So an ANOVA test would be really good if we just have 5 categories. It tests up to 5 categories. That's why we're going to X these pinto beans out. But it tests 5 categories just to say that there's statistical difference between all the categories. And actually, we don't even have to, we'll ask kidney beans, whatever, doesn't matter. So I'm just going to do navy beans through no beans and show you guys how a ANOVA test works. So how I'd have you guys do an ANOVA test, because Sheets doesn't do it. If you have Excel, it does do it, but you might not have that. So we're going to use just click over onto Google and just type in ANOVA calculator online. Okay, most of them work pretty well. I recommend finding a really easy one. This first one that pops up for me is really, really easy. So I just click on this one-way ANOVA calculator. That's what I want you guys to use. Don't worry about anything else. And this one's really easy. You're just going to put in our 5 data points in here. So you just come over to your graph, and I'm going to start with navy beans. Enter my data, black beans. Enter my data. And I'll give you guys a few seconds to catch up. Okay, this test is pretty cool. It lets you pick your significance level, so it's actually going to tell you your answer to your null hypothesis, alternative hypothesis. We would never do a 10%. You could do a significance level of 0.01 if you really want to be close. The standard is 0.05. And you just hit calculate. And it does the test for you. If you did this, you would want to copy this chart. You could shrink it down really small, but you'd want to show this chart and also say what website for your sample calculation. You'd say you use this website. And it runs everything for you, but really all we're looking for is our p-value. We're not going to worry about our F ratio value, but our p-value for this was 0.03. So we would say the result is significant. But all this is really comparing is all of the data together to say that there is differences between the data. A t-test is still needed to see differences between each two categories. So if these were all the same type of bean and there were 4 different layers, an ANOVA test would be really good to say that there's a difference in the gradient. But if you wanted to make any conclusions about differences between 2 categories, you have to run a t-test. I sometimes just recommend running each control or each one versus your control, and that gives you a pretty good idea of an answer. So I would probably run all against a control, but you could also, with this experiment, be like black beans cause more farts than navy beans or something. You could also do that. I hope that helped you guys. Check back in with me if you're struggling. Please, within the next week, really figure out that independent assessment. If you need to get a hold of me, need supplies, anything like that, please reach out, or just want to brainstorm ideas. We really need to get working on those IAs. I know you guys got tons coming, but I don't want to go into second semester and have you guys freaking out that you haven't even done your IAs yet. So we want to get that done as fast as possible. So come up with an idea, make it simple. It does not have to be hard unless you really want to dive into it because you just love doing crazy science stuff. Just get it done.